So here we are back Friday night, and we're back with Vin and Dave's Destination Unknown. Good evening, sir.
Good evening. It is a fine evening.
It is. We got some wine yesterday. Apparently, we have been slacking on our pimping because we're drinking carnivore. And so we were sent. Well, first we can show the wine. Yes. I haven't tasted it yet. Let's see. Oh, that's good. This is Emblem. It's a Napa 2013 cab. It's from Glenn again. This is Glenn's second contribution to the show, and. His note is classic that he included with it, so I figured I'd have to share. He said, "Vin, I can't bear to watch you and Dave drink another bottle of carnivore. So I am stepping in and sending you guys 2 bottles for the upcoming show I think you both will like. Nothing inspires deep thought like a good Napa cab. If other donations arrive this week, feel free to keep these bottles in reserve for a future show, but please, no more carnivore, smiley face. Hope to see you both at the Free Coast Conference in September. Keep up the great work with the show, Glenn." So, Glenn, I actually enjoy carnivore, but I do definitely appreciate this. And as he said, if anybody else would like to donate some wine, we definitely appreciate it. If anybody else wants to see us not drinking carnivore, I guess whatever the motivation is for you to send us alcohol is perfectly fine. Show at vinarmani.com. You can hit me up and we'll work that out. It's a good wine.
It is a good wine. I like it quite a bit.
Wine.
It is it's easy to drink. It's very easy. It's a smooth, relaxed wine.
It's got some complexity to it, though. It's got some astringency on the front. That's nice, little sharp bite, but it's good. It's good. I really like it. So, Glenn, thank you very much, and anybody else, of course, if you would like to donate. So, with that,
yes.
I titled this show "The Strange Story of the Speed of Light."
Oh. Love it.
I think it's a good place to start. We're going to talk a lot about light today. Mm-hmm. We got a lot of light talk.
Light's a weird thing.
Light is a very, very strange thing. This topic came up the first conversation or the first time that we had this sort of wine conversation, you and I. And it was that Step Brothers moment that evening when it was like, did that just happen? Yep. Did we just become best friends? Yep. So
true story.
Right. So I think that it's the perfect topic for us to get into.
I'm glad nobody saw us getting the rulers out though.
Right. So here's variable speed of light. This one tripped me out. So I guess there's 2 sides of this variable speed of light thing. First off, people believe that the speed of light is a constant.
They do, but I'm not sure why. Because it never was. So if you look back at Einstein's early writings, and when he was actually developing general relativity, special relativity, he was going through the creative process, putting all of it together, and he considered light to be of variable speed, particularly in regards to gravity. So light moving through a gravitational field should not only change direction, it should also change velocity, and it is integral into his calculations. He's already done all the math. I am not sure why that has been left out of modern cosmology almost completely.
Well, if you've got a black hole, you figure, and we know that there's an event horizon, there's got to be a change in the... Well, there's a change in the speed of light if at one point the light can get out, and at another point it can't. Because that necessarily means that there's got to be some space where it moves from moving forward... Just like anything, falling backwards or being pulled back, right? That at one point it's coming at you, and at one point it's going the other direction, and that means that there is at the event horizon it's just stuck. Mm-hmm. So that would mean a variable speed of light right there. That would mean that the speed of light could change.
Absolutely, and So it's interesting. The way that conversation, I remember when we were having this discussion the first time, and you said to me, like, do you know why the speed of light is constant? And I'm like, let's see, physics? And you were like, no. There's like this scientist organization. I can't think of the name.
So I've got. I think that's a great place to start this, because it's when I learned this. This is what threw this. It changed my whole world, right? To where I was like, I've actually been right about consciousness being the basis for the universe. Like this was the point, because most people are like, oh no, speed of light. The constant is, what is the constant? The constant is, hold on, because I have a whole bunch of numbers here, because it's been measured in a whole bunch of ways. It is 299,792,458 meters per second.
Yes.
That is the speed of light. So in a vacuum. Yes, the constant speed of light. So that basically requires two things. Well, it requires three things. One, you got to have the light there. Mm-hmm. Then you've got to have two other measurements. You've got to have the time measurement of a second, right? So we've got to agree upon how long is a second.
Yep.
And then you have to have the length measurement of a meter.
Yes.
Now, if you stop and think about it, those are problematic in and of themselves. But let's just imagine. So they have relatively accurate clocks. Most of those are about the decay of certain elements, right?
Cesium atoms.
Yes. So we've got the second. Mm-hmm. That's a certain amount of decay. We're going to say over a certain amount of time. Again, I think that's problematic, and you'll see how that leads into the speed of light. Then you've got the meter, okay? So the meter in 1791 was the adoption of the term metra, meaning measure, because they were looking for a universal measurement, a basic unit of length. So it's defined as equal to 1/10,000,000th of the distance between the North Pole and the equator. So if you're wondering, so how long is a meter? A meter is, you take the distance from the North Pole to the equator. So first off, this is completely subjective to being on the planet Earth.
Sure.
Right? This is not some sort of universal measurement at all.
Yeah, and it's not a sphere. It's it bulges in the middle. I mean, come on.
So you're already talking about like an ideal Earth, right? Then so you take that distance and then you chop it up into 10 million pieces, and if you chop it up into 10 million pieces, then boom, there's your meter. Okay, so at least they're like, here we've got this meter. They've been creating all kinds of very standardized, like a meter piece of metal. This is the standard. So at least, okay, this is a piece of metal. It doesn't really, it's not going to bulge, whatever. It's good enough for government work, right? Here's your meter. You've got your second. So now then the question is, how do you measure the speed of light? How do you start out measuring the speed of light? So they use this thing, an interferometer. So what this does, it takes, because you want some distance, right? So this is they were like, how do we get the best length of measure of a meter to start out so we can run light through it? They use this thing, an interferometer. It basically takes light in the first. So now we're back to like measuring the speed of light with light itself. So it's
all circular,
right? It splits the light into two, moving through particular elements. Every element, it splits the light, brings it back into an interference pattern, and basically what you get like these zebra stripes, kind of. Mm-hmm. And the length of the zebra stripe in between each one is supposedly constant per whatever element you put it through, right?
Yes. Which is super weird, and we'll talk more about that later.
Yeah, that's very, very strange. I know that we're coming up on that. So they did in 1960, they said, okay, we got to figure out this meter thing. How long is a meter? So in 1960, they did, so this is the international group for weights and measures. They said, this is going to be the new meter, 1960. It's 1,650,763.73 wavelengths of the orange-red emission line in the electromagnetic spectrum of the krypton 86 atom in a vacuum. So basically what they did is they made one of these interference patterns using the krypton 86 atom, and then they said, okay, those stripes from one stripe to its next stripe, a wavelength, it is 1,650,763.73 wavelengths. That's a meter.
They couldn't round it off? I mean, come on. Seriously. Who would have known?
But this is exactly the fact that you say that is why the whole speed of light thing is I'm like, oh, you guys are nothing but bullshit. Because in this case, they're like, we cannot round it off. 0.73 even. 0.73. It's got to be. We cannot round it off. Okay. So this is 1960. So now they've got the second. They've got the meter. Now people are like, let's measure the speed of light. Let's see how fast it really is. Because up until that point, they had never... Now all of this thing with the meter is all to measure the speed of light, mind you. That's why they're concerned about this meter. It's all to measure the speed of light. Because they're like, it's got to be a constant. How maybe the reason that every time they measure it, it's never showing the same thing. Mm-hmm. They never get the same thing. And they're like, maybe this experimenter's meter is wrong. Like, maybe he's got the wrong meter. We need to standardize the meter. They keep measuring, right? Still doesn't come back as the same thing. Never a constant. And huge margins of error, mind you. Huge. So then they're like, okay, we've got it. They start measuring. So the last time that they actually measured the speed of light, or even tried, this is interesting. The last time that they even tried was in 1972. They were using the laser interferometer, that same method. They were using all the new definitions. Boulder, Colorado, the National Bureau of Standards determined the speed of light in a vacuum to be 299,792,456.2 meters per second, plus or minus, so a margin of error, 1.1 meters per second. It was 100 times less uncertain than the last time that they had done it. Some of them had wildly plus or minus 9 meters per second, which is wow. That was the last one that they had done before that, which is yeah, that's 18 meters per second. That's a non-trivial speed. That's faster than the speed of Usain Bolt. So that's not going to work. That's not going to work as a margin of error, right? So they said, okay, the remaining uncertainty, this is the narrative. The remaining uncertainty was related they say, to the definition of the meter. Okay, but here's where it gets really crazy. So they keep going. So that's in 72. They keep trying to measure this thing, right? It's still that's the best that they're able to. They tell everybody stop measuring. We got to get this meter thing figured out. 1983, the 17th General Conference of Weights and Measures. They go into this thing and they're like, we need to get the speed of light correct. Now, mind you, it's meters per second. What they do is one of the biggest pieces of chicanery in all. Really, it's not even science what they did. So they were like, it keeps changing. It keeps changing. So what are we going to do? They said, this is their main resolution of the whole time. So they call this conference. Everybody gets there. They put together this document. And it says, considering, 1, that the present definition does not allow a sufficiently precise realization of the meter for all requirements. Basically saying, our current definition of the meter, there's something wrong with our current definition of the meter. Because we can't get the speed of light measured correctly, and the speed of light, we know it's a constant. So it must not be that the speed of light isn't constant, because it must be a constant. It must be that our meter is messed up. The meter must be what keeps changing. So then they said, considering that progress made in the stabilization of lasers allows radiations to be obtained that are more reproducible and easier to use than the standard radiation emitted by a Krypton 86 lamp, and that the progress made in the measurement of the frequency and wavelength of these radiations has resulted in concordant determinations of the speed of light whose accuracy is limited principally by the realization of the present definition of the meter. So basically, we keep doing all these measurements, but they're messed up because the meter must be messed up, because the speed of light is... So they go into it like, no, the speed of light is a constant, which is completely unscientific. If every single time you measure something, it's not constant, maybe the first thing you say is, well, maybe it's not constant. So then they say...
Or they could have listened to Einstein. That would have been smart.
They could have. They could have. So it says... so it goes on, that these various forms, making reference either to the path traveled by light in a specified time interval or to the wavelength of a radiation of measured or specified frequency, have been the object of consultations and deep discussions, have been recognized as being equivalent, and that a consensus has emerged in the favor of the first form. So basically what they're saying is, we have been measuring, so they've been doing this measuring of the wavelength, and they say right here, various forms making reference either to the path traveled by light in a specified time interval. So basically what they're saying is, okay, the speed of light is this amount of meters per second that light travels. But if you flip the equation around, if we know that that's a constant, they're like, well, then we should just be able to say that the length of a meter is just how, if light is a constant, then the length of a meter, and that's basically what they did, that they're like, we've decided the meter is the length of the path traveled by light in a vacuum during a time interval of 299,792,458th of a second, and that the definition of the meter in force since 1960, based upon the transition between the atom Krypton 86, is abrogated. So basically what they said was, we are just going to say that the speed of light is not how many meters per second light travels. No. We're going to say that the length of a meter is however long light travels in a second. So that's like me saying human beings walk at 4 miles per hour. So then it's like, well, how long is a mile? Well, a mile is however far a human being walks in an hour. Or it's however long they walk in 15 minutes.
Yeah.
Right? If a human being walks for an hour, or for 4 hours, however far they walk, that's a mile. However far a human being walks in a quarter of an hour, that's a quarter mile.
You know, the science is settled. I don't know why you're asking questions about this. I mean, this is obviously, settled science.
It's just so ridiculous on its face to say that it makes absolutely no sense. You simply don't measure speed that way. And what they basically did was they just said, no, the speed of light is this because we say it is. That's literally, it's a very, very fancy way of just saying, you know what? No, we figured out a little trick, a little sleight of hand here to just say the speed of light is a constant. You're going to go by that. It was by fiat, completely by fiat.
Yep. But that's how governments do things.
But this isn't even a government like this. I guess it's a government agency. I mean, it's a multidisciplinary international agency.
That sounds like a lot of governments. Oh.
But that is I mean, it's a trick. It's a trick.
It reminds me of, so why is this necessary, right? Like, why did they go through all that? I mean, they convened a lot of brain power and a lot of money to write that.
And this was the only, well, what's interesting is that, this is basically the only thing that they convened that for in 1983. And it says what their annual appropriation is for this organization. Because at the end of this same whole, their resolution for 1983, of course, there were 4 resolutions. The first one was about changing the meter. The second one was about we need some more working groups to figure out how to disseminate this thing about the meter. The fourth thing was the budget. Their annual budget, 1985, 13 million. In 1985, 13,144,000 gold francs. Now, I'm not sure what a gold franc is.
Wow.
I don't know what that is, but I'm assuming it might be like $1.
I want some.
I don't know, but it's like and then the next year it's going to be up by another 1.2 million, and then the next year it's going to be 1.2 million. So by 1988, this organization, 17 million gold francs for the year, and this is the shit that they do. They basically can convene to say, yeah, we need a place to start here, guys. So we're just going to start with the speed of light is a constant.
Mm-hmm. But why? Why was that important? The reason is because the math, right? The math's hard. And in order to make it easier, you simplify things. And one of the biggest simplifications is establishing the speed of light, using spheres, talking about everything in a vacuum, to the point where there's actually a joke, and I looked this up because I wanted to get it right. So milk production at a dairy farm was low. So the farmer wrote to the local university asking for help from academia. A multidisciplinary team, sounds like the same group that wrote that document.
Yeah.
They were assembled and they headed over. Their leader was a theoretical physicist.
Okay.
And 2 weeks of intensive on-site investigation took place. The scholars then returned to the university, notebooks crammed with data, where the task of writing the report was left to the team leader. Shortly thereafter, the physicist returned to the farm, saying to the farmer, "I have the solution, but it works only in the case of spherical cows in a vacuum." And I think that's the essence of this whole thing, is that they're looking for, a defined constant so they can eliminate any of that variability from the math, even though it's been in the math since Einstein.
Now, but to me, the problem is it's more of a human issue. And the human issue is, like, why is this hidden from people? Like, why can it not be out in the open that, like, actually, guys, just so that it actually isn't constant, but we needed this for the math.
But there are so many things like that. So much of physics is about figuring out how to do the math in a simplified way, so that way it works. And so there are a lot of constants out there, and there are a lot of things that we don't have independent ways of measuring. Like, if we had a way of measuring the speed of light that didn't involve also measuring the speed of light, it's a circular reference,
right?
So, I mean, it's fast.
But everything is subjective. I mean, even to talk about speed, because the question is, they say, and of course we would say, yes, the sun orbits the Earth orbits the sun is orbiting around the middle of the galaxy, but it's like, yeah, but it's got to be relative to something, because it could just very well, it's not like there is some objective fixed grid location in the universe. I mean, the Earth could just be sitting still and things are moving around it. I mean, it really is just a matter of perspective.
Sure, and they refer to that as the horizon. Well, they refer to a version of that as the horizon problem. So the thing is, with an expanding universe, no matter where you are in the universe, it looks like the entire universe is expanding away from you. I think that was one of the most interesting things about VSL theory, variable speed of light theory, is that it's actually come into prominence again over the last 20 or 30 years. So it started with Einstein. Einstein actually included it in his calculations. He believed it. He proved it. I mean, through the math. The math is there. The work is there. He assumed that if you had gravitational lensing happening, which he predicted, where the light was being bent, that the light speed would also be affected at the same time. There were some people that disagreed with that, but he did have Max Born and Richard Tolman both agreeing with him and saying that not only the direction of the light but also the speed would have to change because you're going through a gravitational field.
But nobody knows what gravity is. Let's be real. Nobody knows what it is.
And I don't think anybody knows what it is for real.
Right.
It's the best. I'm a huge fan of Einstein, and when he described it as the fabric of space-time, I don't know that anybody's ever done a better job of describing it than that, and I don't really know what that means for sure, and I don't think anybody else really does.
Like, does anybody really know what space means? Does anybody really know what time means? I mean, I feel like look, you're right back at your meters per second because that's what you're talking about. You're talking about space and time, and clearly these things they're very difficult to measure for real in any like real, meaningful, precise way. You can get some approximation that's good enough, but I mean, that's on every scale because it's the same thing as like, I could say, okay, here, my fingers are together. Like my thumb is touching my, pointer finger. That's true at my scale, at the Vin scale, but certainly, like, as anybody knows, like, I could put some oil or something, some olive oil, and move my hands like this, and clearly there is a film of something that's in between, but they do feel like they're together. And if I was a small enough Vin, I could, well, look, if I was the size of an electron, it would be like a vast amount of space.
Oh, yeah.
A vast amount of space in between. I mean, a galaxy's worth of space in between. So it's like even that distance is completely a matter of perspective.
Absolutely. And, us saying that, time is a big mystery isn't just us being dumbasses. It is
actually... It's a little bit of that, too.
It's always a little bit of that. But it is one of the major unsolved problems in physics why there is an arrow of time, right? Like,
or is there an arrow of time? I think that's maybe the real question.
So time appears to exist.
There you go.
And it appears to only run in one direction. Why? Nobody has an answer to
McKenna said novelty theory.
What did he mean by that?
So McKenna's idea was that we can only tell that time is passing because something is changing. So he basically has this theory that, like, over the course of time, quote unquote, that basically what happens is that new things arise in the universe. It's like entropy, right?
Yep.
So it's like it's not that things are necessarily breaking down so much as novel things are appearing. And that it's in the novelty that it appears, and that's why it appears that time is speeding up. Right? So it's the reason why we talk about you've got this long period of time after the Big Bang when you have basically this sort of like soup, right, of just a cloud of matter, and then it's a shorter amount of time that the stars come into being, and it's a shorter amount of time but still a very, very long time that these planets that the concrescence happens and these planets come into being and separate from themselves. And then if you come down to the sort of Earth span of time, it's a shorter span of time then before the Earth comes and comes out of its sort of purely volcanic phase and things sort of separate out, but it's a less amount of time than it took for the planet to come together. And then so on with life, and then so on with complex life, and then so on with, for instance, mammals coming about, then so on with human beings, and then in the span of human beings, that it's like we even see, for instance, that the who was just I just had Gabriel Cardona on my show, and he was talking about Kurzweil's singularity theory, and the idea that somebody who lived from who was born in 1900, let's say they lived to be 100 years old, and they died in the year 2000, right? So they saw, the first electricity, they saw 2 world wars, they saw it go from horses to people on the moon, they saw, computers, the internet, like all of these, that century so far was the greatest advance.
Yeah.
Right? But someone living today, if you look at the technological advances, someone born today will see the equivalent of 20,000 years of advancement in their own lifetime.
Assuming nothing goes wrong.
This is what I'm saying. If nothing goes wrong, but that may be part of the 20,000 years itself. Whereas, somebody who was born in, say, 1100 and they died in 1200.
Nothing changed.
The world didn't change. Not only did the world not change, they lived pretty much the same life that the person born 100 years before them, who died at the age of 100 when they were born. Their world was pretty much indistinguishable. Mm-hmm. Some little tiny, tiny, tiny changes. But it's like the world now, if you took somebody from 100 years, from 1918, from just after the First World War, mm-hmm. and you drop them in this world, they'd lose their fucking mind. They wouldn't be able to operate. They'd probably go crazy just from the stimulation, just never having had this level of stimulation before. And so this is the idea of this novelty theory, is that it's like time, what time is really about is it's a measurement of the emergence of novelty. And he's got this idea that there is this, that basically what happens is that it's the singularity. Like McKinnon was pretty much the first one to talk about this idea of the singularity. Like what does he call it? He calls it it's a beautiful phrase, the something at the end of time. Well, it's the eschaton, it's the eschatology, right? But it's like it's not the big bang, but he calls it the big surprise. But it's kind of like where you get to a point where where there's so much novelty that there can't be that nothing new can actually come about. And you come into this like layer of concrescence where it's like everything, it's becoming so new that it's like absolute, can't comprehend, consciousness is out of bounds, like all of that. That's the singularity, I guess.
Wow. Interesting.
And he says that's what time is. But his idea is that while the arrow of time is in one direction, we might think that it appears that it's being pushed from behind, right? So that each new thing is then creates another new thing, right? So that things evolve. His idea is that it's actually being pulled from the eschaton.
Oh.
That it's being pulled to that final thing as opposed to being pushed from behind.
Like time's version of dark matter or dark energy.
Kind of like that. That really that you think the arrow of time is going, like you're not on a train, right? The train has no engine. There's something out there that's pulling you towards it. And as it pulls you, it's pulling you through this sort of strainer of novelty. And it's just things get new. That's his concept. It's pretty trippy. I mean, the dude also, took heroic doses of mushrooms, so yeah.
No,
Take it with a grain of salt.
No, it's interesting, right? I mean, especially when you think about that sort of thing in the context of like simulation theory. And are we in an ancestor simulation and we're just playing through a script that has possibly been played through 1,000 or 1,000,000 times before? We don't know.
Well, and who's to say in that regard, like it could, why does it have to be playing forward? Like we might think it's playing forward.
Sure.
But why could it not be playing in reverse?
Or at any point in time, anybody wants, I mean, you skip around, do whatever you want. Play backwards, play
Always
forwards.
goes back to the holographic universe. Always goes back to the holographic universe. Yeah, I mean, time is very, very strange. And I mean, we have, just for me, like being sort of dream time, right? That you can experience, what seems like a day or a week in a span of minutes. Which makes me think, well, if that's the case, and if the whole deal with time is that it's being experienced, like then even time can't be a constant in that regard, right? I mean, isn't it really human consciousness that's determining time?
Well, and time isn't a constant. I mean, even, according to Einstein, it's surprising that physicists were able to jump on that time was not a constant, but they couldn't jump on the train with light. It would seem to me to be much more strange that time slows down when you go faster. That's a much stranger concept to me than gravity slowing down, light slowing down in gravity. So, yeah, I mean, variable speeds of time based on the observer, based on, even the experience of the person that is traveling fast, right? I mean, they are experiencing a much slower clock. Their lifespan is going to be much, much longer.
But that's the question. Are they experiencing a slower clock, or is it just a slower clock relative to another observer, right?
Sure.
So they're living out their life, and it appears to them that their clock is running at the normal time.
Yep. But, back on their homeworld, things are going 2, 3, 4 times as fast.
Yeah, that just says right there that there has to be this consciousness element to it, because that means that there are literally infinite arrows of time, and perhaps there is an arrow of time that goes backwards. Like perhaps that means that you could travel in some manner. I don't know what that manner would be, but you figure if time can slow down, we know that certainly light can, within a black hole, not be able to escape. So we know that it can basically go in reverse. I mean, it has to be in reverse. That's the thing. In order for it to be a black hole, the light has to be traveling. It has to be trying to get to you, and it has to be traveling then away from you, right? But it's not. Do you understand what I'm saying? It has to be, because if even if the light was not moving, well, no, then it couldn't get to you, right? It could never get. So that would be black too. Maybe the light's just not moving.
Yeah, and I think that also is part of what Einstein was working on. Like, light can literally stand still.
Yeah, that's a trip. The photons would stand still.
Yeah, but in the sense of a black hole.
The thing is, you'd be dead though.
Right. Nobody wants to go in a black hole.
Well, or would you be dead? That's the question.
I'm going to go with yes, but I will leave the possibility open that we don't know everything we should know about those things.
Well, doesn't death require time? Like, doesn't in order for you to experience death, isn't there a time element there?
Sure. Yeah, I mean, you're actually... So this has always been something that I have puzzled over, right? Like, I know that, like, for me, I can feel time slowing down. It's like if I know that, oh, man, I got to go into see the doctor. You're sitting in the waiting room. You're going to go and see the doctor. You know he's going to put on the rubber glove. And you're like wanting to stretch out that last 5 minutes in the waiting room while you're reading Time magazine. And it's just like, you can stretch that out and make it last it seem like it lasts a long time.
Or that last 10 minutes before you're like, before you know the alarm is about to go off, but you're still tired.
Yeah. Yep. Or the 5th time you hit the snooze.
Right.
Yeah. So I'm just like, I would imagine that same kind of thing, as long as you're not dying in a car crash or some, like crazy, like instantaneous deal, if you feel it coming, can you actually, like, how much can you get out of those last few minutes?
Well, I mean,
I would think a lot, because that's,
I think that's maybe what the life flashing before your eyes sort of situation would be. Well, or do you even, again, because like, is it that the perception of time is actually a sense? Is it a sense? And if you lose that sense, then do you lose that perception of time? And clearly we do lose a perception of time when we lose consciousness.
Mm-hmm.
Right?
You can go to sleep. So yes, the time sense is an actual sense. It's one of the, so if you look up, articles on the senses, that, the 5 senses, whatever, there are actually a bunch, and time is one of them. And you can have specific kinds of brain damage that prevent you from experiencing time the way that other people do. It doesn't mean you have any kind of superpower. It just means that you're not aware of its passage, or you're too aware of its passage. And, or you're unable to retain short-term memories. there's a lot of different
things. Like that Memento movie.
Oh, yeah, great movie.
Great movie.
Love that movie.
Yeah, Guy Pearce.
Oh.
Yeah, poor man's Brad Pitt.
That makes total sense. Yeah.
Skeet Ulrich is the poor man's Johnny Depp. There's a poor man's everything, but he was great. Guy Pearce was great in that movie. He was absolutely that where he tattooed all the things onto his body.
It was awesome.
And if I'm not mistaken, that movie actually doesn't. It's disjointed, right? Mm-hmm. It's out of. So he's actually experiencing, or we're supposed to get the idea that because you would think that that's pretty much what it is. If you've lost your short-term memory, so you've got some past experience that you remember. That's maybe the last thing that you remember. And then you have a disorder, a traumatic brain injury or something, right? An infectious disease, something that takes out that particular piece of the brain. That's got to be absolutely terrifying. The idea that, there's that last thing that you remember, and then all of a sudden, okay, where am I? But who knows how long could have passed? Yeah. And you're different, you're older. It's like, but you imagine having that and then actually growing older. Mm-hmm. Right? To where it's like, then you are like, whoa, who is this? Like, what is this body that I'm in? Like, it's a very, very strange concept.
One of the weirdest things for me is that honest to God, I don't feel like I've aged since I was in my late 20s. Like, I remember, being a teenager. I remember doing, all the teenage stuff. And then I got married very young. But then, like, somewhere in my, mid 20s, I turned 40, and I've just been there ever since. And, honest to God, I still, now I'm past 40, but I still feel, I actually feel better now than I have in years. But the passage of time is such a weird phenomenon. I literally feel today like no time has passed. I think of 10 years ago like the 90s.
See, and this is sort of what I'm getting at, is that it's like outside of sort of the natural biological limits that we have on our body, I don't think our consciousness is really I don't think it's very good at doing the time thing, man. It's really not.
No, and I don't think your brain ages in the same way that your body does. People end up with aches and pains and whatever. And I've met people that were 30 years old and were old. Like you could tell, like,
oh yeah,
not just physically, but like mentally, they were just beat down. They were old.
Yep.
But then you meet, some, 70, 80-year-old dude who's like skipping in the rain, and it's like, I want to be that guy,
Yeah, it's, it is definitely, again, these things trying to nab these constants. In some ways, I feel that there's I wonder where that comes from. I wonder where, because I'm always interested in the human element. I wonder where the desire comes from that, the individuals who are in this general conference of weights and measures and do all this.
First of all, why would you get that job in the first place? Like,
well,
hey, Mom, I want to grow up to become a, weights and measures person.
Well, I'm assuming that you probably end up in it, but there have got to be some people for whom they are obsessed on this.
Oh, yeah.
And who really genuinely feel that it's like the most important thing that could possibly happen. Like that 1983 meeting where they did the thing with the meter, that there was some heated discussion where people really found it to be super important, that it's like, you don't understand. It's so important. You don't understand how important it is to the future of science and the future of the world that we just set this meter, we set it where it's supposed to be, we have the speed of light at a constant, like we have to do this. And for me, I'm like, who is this person?
If we don't know how long the meter is, how will we know how long to build the roads?
Roads. I'm glad we got some roads in here finally. Okay, so I know that you have quite a bit here. You've got some other weirdness.
Yes,
I'd like to get into it.
Let's do it. Let's do it. Let's do the weirdness. I made a video.
Okay,
believe it or not.
You've been talking about this video, and so I'm very interested to see it.
So,
do you want to promo this video about what it is that we're about to watch? Don't worry, for the people who are checking this out on podcast, we are going to narrate through. We may be pausing it at certain points, I've been told. So, okay, go ahead. Tell us what we're about to watch.
So Paul Dirac was a physicist, one of the founding fathers, if you will, of quantum physics, and genuinely brilliant guy. Einstein referred to him as, balancing on the edge of madness and brilliance. And if Einstein is saying the guy is brilliant, I take his word for it.
Or mad.
Either one,
right.
And with this guy, apparently it was hard to tell. But, he did significantly contribute to the field. He won the Nobel Prize with Schrodinger. It's like every once in a while you run across, and we were talking about this earlier, every once in a while you run across one of these like uber geniuses. And the weird thing was they were all in Germany all at the same time, working on the same thing. Very coincidental, It's like, what were those guys all doing there, working on the same stuff at the same time? Before the World Wars. So, very, very weird. So Dirac came up, and he did this in his head, which is phenomenal to me. He wanted to demonstrate some of the fundamental properties and features, if you will, of quantum mechanics, and he came up with this very simple experiment involving polarized lenses.
Okay.
And so I made a little, educational video, explainer video, I guess is what they call it.
Okay.
And let's go ahead and crank it up. Yeah. And we'll just kind of talk our way through it. We'll pause. We'll see what's going on.
Okay. So this says Dirac's 3 polarizers. Are you going to go ahead and narrate this here?
Sure. So I'm not going to do it word by word because, it's going to go fairly quick. But so Dirac, like I said, one of the, brilliant founders of quantum physics. You can do this experiment yourself. This is something that you can do if you have polarized sunglasses, or if you have the old style linear photographic filters, easy to do yourself. Or you can just watch my video. So light is an electromagnetic wave, right? It has an electric component, a magnetic component, and they are oscillating at right angles to each other. So based on how how the electric field part of it is oscillating, we refer to that as being either polarized or unpolarized, right? So polarized light is oscillating in a single direction. Could be any of the directions, but it's a single direction.
Okay.
Unpolarized light does not have any particular direction. It's oscillating in all the directions. So when you run light...
Okay, wait, let's hold
Yeah, let's pause for a second.
Pause. Okay. So we've got polarized light and unpolarized light.
Yes.
You say there's magnetic and electric. You have this sort of oscillation.
Right. So an electromagnetic wave of any kind, not just light, but of any kind, is going to have an electric field component and a magnetic field component.
So we're talking everything from radio to X-rays to gamma rays to cosmic rays to visible light to infrared. Okay.
They're all on the spectrum.
All on the spectrum.
So
probably like
us.
Yeah. There we go.
There we go. So so you have this, this electric field and this magnetic field at 90-degree angles, and the polarization actually is in light is specific to the electric field and the way that it is oriented. So if you're looking, imagine if you're looking dead on at a light wave duality, particle duality thing,
All right.
which we'll talk about in a minute. So if you got like an XYZ axis, right? So if you get your electric field and your magnetic field, and then you can turn it, so it's still like if you're talking about a beam of light where they're all oriented the same, then it's polarized.
Okay.
But if, this photon's this way and that photon's that way, and
so if it's just kind of jumbled around.
Yeah, they're all randomized, then that is unpolarized. Now, each photon will have a polarization, but the group of them together are not coordinated in any way.
So when you have a polarized lens, what you're doing is you're only allowing photons through that are traveling it's like a filter in a way.
Indeed. And in fact, that would be very helpful to think about it that way during the first half of the video.
And we're in the first half, so.
Woohoo!
Here we go. Carry on.
Yep. So unpolarized light comes from both natural and artificial sources. So I actually have this really awesome drawing of a light bulb, and it is actually shining light that is unpolarized towards a polarized filter, and everything's labeled. There's like arrows. It's phenomenal. So then the polarized filter is sitting there. And then you can see that on the other side of the polarized lens, the filter, that the light is polarized. It's only oscillating in one direction at that point.
Okay.
Cool. So then what do you think would happen if we inserted another polarized lens after the first lens, but we rotate it by 90 degrees? So what we're going to have, let's call it vertical and horizontal.
It shouldn't let anything through then, I would think.
Correct. So if we are aligning everything vertically, right, and then we put a horizontal filter in front of it, nothing should come through.
That's what you would think, yes.
And let's find out the answer as it is revealed on the screen.
So basically, hold on, before we get into this,
go ahead.
So that people can kind of play along at home. So what we're talking about is, what we're looking at here is, so the light bulb is shining through, I guess that's just like a piece of glass or something like that.
Yeah, it was just to show the direction
Right. So it goes through the piece of glass. There's like, it basically looks like I don't know, it's like a cross and then an X, right? So you've got like, light is traveling in it's polarized in every direction, right?
Or any direction.
Right? But there's every direction, it's kind of like all over the place. Then you put a polarized filter, and this polarized filter, in this case, it looks like it's just vertically polarizing it. So when the light sort of hits the next piece of glass, the only polarization that we see, so instead of seeing this star or this X with the cross, right? So you imagine just make a cross and then make an X like a compass, right? So you've got the 8 sides or whatever, but it could be a million of them. in this case, what we see is we just see the north-south line.
Yep.
That's all we see.
Yep.
So then what we're saying is if you then put a east-west polarization, basically what we would expect, so you imagine that the filter is almost like a slit that's going up and down. And so all you've got is this up and down,
like a picket fence kind of thing.
So yeah, so you've got something traveling through the picket fence. So then you figure if you were to put a crossways one, it should just hit that and not be able to go through. That's what you would think, because it's up and down, and that was all that was let through on the first one.
Yep.
So clearly it didn't let through the side-to-side ones.
Yep.
So then it's coming. Okay, so let's see what happens.
All right, so let's see what happens.
So there's our little filter.
Yep.
Polarized east-west.
Yep.
Goes through, or doesn't go through. I don't know. We're seeing.
All photons are blocked. You are
All
absolutely
photons are
correct.
blocked. Okay,
Yeah.
boom. Okay,
See?
good. So
Excellent.
that's good. I thought this was a trick, but
well, here's the quiz.
quiz time.
Yeah.
Okay.
All right, so what do you think would happen? And you're probably going to want to pause after it finishes drawing. But what do you think would happen if we actually added another polarized lens in between the two that we already have, right? So we had the one that aligned everything
up and
vertically.
down, okay.
Yep. And then we have the other one that aligned everything horizontally, or would have if it had allowed anything to pass.
And that'll be the last one, right?
The last one. And so then we shove a middle interloper in there diagonally. So you would think
It just block it.
we're just going to block more light, right?
Yeah, it is. I mean, it's got to be the only thing that'll get through is up and down. If you've got a diagonal, it's going to block the up and down for sure. Like that. Well, clearly, if the side to side blocked it, you would think, right?
Yep. So the question drawn on the screen is what photons would exist immediately after the second filter, the new second filter,
None.
and then what photons after the third filter?
None.
So now we get to find out in this awesome live video that I've actually put inside this Instructable video.
Oh wow.
That I filmed myself. So I have 3 polarized lenses
Okay.
that I put on top of an LED screen.
Okay.
And the first thing I'm going to do is stack them all up so that way we can see, look, they are all aligned. I even put little sticks on them so you can tell what alignment they were.
Okay.
So I take the top one off,
Okay.
right? And now what I'm going to do is I'm actually going to turn the top one 90 degrees so you can actually see all the light is blocked.
Yep.
So
I
you
see
have
that.
the vertical, and then it's being blocked by the horizontal.
Got it. Okay, that's
right.
what we expected. That's what we saw.
That is exactly what we expected.
Okay.
So here comes our interloper. Oh, what happened? We have light. Oh my! Oh, how did that happen?
Possible?
How is that possible? This is the weirdest thing, right? So I actually have a 3-way thing. You can pause it once that stops. So what we have on the screen is I was actually able to get an overlay that actually shows a single lens, the front one and the back one together, the front one and the middle one together, the front, middle, and back together, like all of them, all the different combinations in one picture. It's pretty snazzy. But yeah, you can clearly see that just the first and third filter, total blackness. There's no photons coming through. But in the middle, where you actually have all 3 filters, there's a significant amount of photons coming through. I mean, that's not just dim light. That's a lot of light.
Is it because the 45-degree angle when we use, so we're talking about like northwest to southeast, if we use that thing, it doesn't, so maybe it's only fully blocked when it's 90 degrees, but when it's 45 degrees, it lets a little bit through, and then in terms of orientation, it's still 45 degrees, so it should let the same ones through, right? Maybe?
You would think.
I don't know.
And
I mean, I don't know. I'm just looking at it, and that's how I would explain it, by looking at it.
Mm-hmm. So it is fundamentally weird, and this is why this right here is why Dirac conceived of this, because it is something that, honest to God, I spent like $8 a piece for these lenses. Like you can pick them up on Amazon for next to nothing.
Yeah, you said he did this in his head.
He did it in his head.
He knew this would happen in his head.
Yeah.
So what was it that he said was going on? Should I hit play or?
Yeah, let's go ahead and let's go ahead and hit play. and we'll go on to the...
So people who are watching on a podcast, you're probably going to want to go onto YouTube. This is episode 7. You can go to youtube.com/VinArmani. Or you could just type in into YouTube search Vin and Dave's Destination Unknown, The Strange Story of the Speed of Light, episode 7. Quantum
superposition.
Okay.
This is one of the fundamental concepts of quantum physics. And so once this draws out, I'm going to talk through this. Once that draws out, go ahead and pause it. But basically, according to Dirac and quantum physics, the polarization value for all the photons exists in a state of superposition until it is measured. For example, let's say that we measure a photon and determine that its polarity is plus 45 degrees. And we'll just use the same kind of numbers that we've been using in the demo.
I missed it. Hold on.
Oh, that's okay.
I'll just go back. Cool. Okay, go ahead.
Awesome. So, this would imply, right, like before measurement, that the photon's polarity was in a superposition of all the values between 0 and 90 degrees. Because remember, we have the 90 degree plane or the 90 degree offset oscillating fields. So anywhere in a 90 degree range, there could exist the polarity of this particular photon.
There could, or it does.
The polarity is there. We don't know what it is, and we don't actually know if it'll be blocked, but I'll cover that.
But wait,
shortly.
Of course, but we do know that it'll be blocked because you just showed the two things, so we definitely know how we can block it.
Yes, probability, and I actually explain that next too.
Okay, go ahead.
It is fundamentally weird, I'm telling you. All right, so if we have the polarity in a superposition of all the values between 0 and 90 before it's measured, then if we do measure it, where was I? And it's 0, right? The polarity prior to measurement was all the values, and the measured polarity, right, comes out to be centered on where the superposition would have been.
Is this Schrodinger's cat? Is that what this is?
Yeah, the Schrodinger's cat, with whom Dirac actually shared the Nobel Prize, is a real-world thought experiment about superposition. But I actually think the polarizer thing does it better because I like cats.
Fair enough. Do you want to explain Schrodinger's cat? I always get it wrong. It's something about you've got a cat in a box and you drown it or something like that?
No, you just got a sick cat. So it's a sick cat.
Sick cat.
Well,
okay.
So I've heard it told with you have a sick cat and you know it's going to die, but you don't know when it's going to die. So you lock it in a box, and until you actually open the box, you don't know whether it's dead yet.
So it's both. So it exists in a state of... Technically, it exists in a state of both. That's what Schrodinger said.
Yes.
It's both alive and dead in the box.
Right, and you can't tell until you measure it, which you open the box and you see. And the other one was that you actually put a vial of poison in there with the cat. And, and I'm just like, man, these people just hated cats.
I think it's a German thing. They're just morbid. I think they're just morbid. So this is the idea. The idea is that when you don't measure it, it could exist from it has all of it from 0 to 90. It has every value, and then when you measure it, that's when the wave function collapses and it coalesces into a specific value. But see, I'm not. It's like the Schrodinger's cat thing. Like, it's not. I know that okay, Nobel Prize, cool, but it's like, no. To me, I'm like, no, it does not exist in all of these. It's gotta be one. Like, it doesn't make. So I'm trying to understand how this explains that.
Well, those kinds of thoughts plagued a lot of the early physicists who were coming up with this stuff because they hated the idea that the world was indeterminate, but yet that's what they kept finding. they didn't like it. They didn't like the implications. They didn't like, what it could mean.
But I feel like this is an ancient, like the Zen koan, if a tree falls in the forest and there's nobody there to hear it, doesn't make a sound. I feel like people have been toying with this for a long time.
They have. And the whole idea behind, how much of life is an illusion? Is it all an illusion? Is part of it an illusion? How much is actually controlled just by what goes on in our heads? Are we living in a simulation? Those, it's like we're not the first people to talk about these things. These things have been talked about for thousands of years in one form or another.
Okay, so go on with this, because we still have a little ways left on this demonstration. So where were you? I'm sorry. I feel I'm interrupting you here.
No, dude, you are interrupting in the way that I wanted you to interrupt.
Good.
So it's all fantastic. So what this is telling us, in a nutshell here, is that the polarization of a photon not only isn't known, and not only that it can't be known, but that it isn't even really established until it encounters the first filter. When it hits the first filter, that's when we lock in a polarization.
Okay.
So, what happens when our happy little bunch of photons hits the first filter? Their wave functions collapse, and all their polarity values, which had been superpositional until now, they get locked in, right?
So they get locked in at the 0, if we call it 0 to 180.
Yeah, because the first one's, actually it's
down.
negative 45 to positive 45.
Okay,
so the one on the left.
Yeah.
Because we first hit the vertical filter, right, so it was superpositional. Now we're locking it in. So depending on whatever value they have, right? Like they had a value, or they once they encounter the filter and are measured, then they have a value. And how close that value is to, what the filter wants determines the probability of the photons. And I don't want to say passing through, because that's not actually what happens. What happens is they are absorbed, and either they are emitted as heat or they are re-emitted as a photon out the other side. So the filter absorbs the light energy, right? And then, based on, how...
So it's not the same photon that comes out on the other side?
It can't be.
What?
That's the magic of the whole third filter thing. These are new photons with whole new superpositional polarities.
Okay. So it's hitting the glass on one side. And by hitting the glass on one side, it's knocking photons off of the other side?
Right, because the way you make a polarized filter, at least the way Polaroid does it, is that they actually use iodine stretched across a thin film of PVC, I think, some kind of plastic. So what happens is that they stretch it in a single direction, and that becomes the direction of polarization. The iodine atoms actually have 7 valence electrons, so they very easily absorb and re-emit energy. So because they have so many valence electrons,
yes.
This
is how you make organic solar cells. I've done this before.
Yep.
You use a little bit of iodine, some dye, some plant dye, some titanium dioxide, and it'll emit energy. But it will also allow light to pass through. It's like they were working on this for a long time, solar generating windows, tinted windows. So I guess that must be polarization that it's doing.
Could be. You still get, most of the light still comes out the other side.
Yeah.
It's just in the form of new photons.
Interesting. Okay, so I'm looking at this graphic, and it's kind of making sense to me. So like you kind of got these little Pac-Mans here.
Right. So if you take a look, the reason why we didn't get any photons is that if you look at what the filter wanted versus what the photons had, right? So if they've passed through the first filter, they're all going to be superpositional between negative 45 and plus 45.
That's right.
They hit the second filter, which at that point in the experiment was horizontal, right?
Right.
And it says, I only want the ones between plus 45 and plus 135.
And there are none of those.
There are none. So because there are none, the probability of any photons getting through is 0.
Right.
So then we introduce the third, which actually went in between the two filters,
right,
or the two lenses. And so that filter said, hey, I'll take anybody that's between 0 and 90.
So it's a Venn diagram. So so you cut it into quarters, but then that one gets an eighth of either one. And so you think that's weird though. So what's coming out, but what I don't understand on that is like it still doesn't make any sense to me. Oh, because the photons. Oh, because that is the proof that it's not the same photons,
right,
isn't it?
Yes, they're new photons because now they have an overlap. The second, by inserting the middle filter, we've created new photons.
See, we're calling it a filter, but that's not the right word.
It's a polarizer.
Yeah, that's not the right word for what's taking place there. What's taking place there is way more complex than that. That it's like photons are hitting one side and they're basically like knocking photons off of the other side.
Yes, that have the new polarity. Of the orientation of the lens.
I did not know that. So is that how polarized sunglasses work?
Yes, exactly.
So basically, when you wear polarized sunglasses, the light that is hitting your eyes is not the light that came from outside of the glasses.
Technically, no.
That's weird. The light that is hitting your eyes when you wear polarized sunglasses are photons that are being basically knocked into your eyes by the photons. So the photons hit the polarized lens. They don't pass through it. They knock photons off the backside of the other one, and that's what hits your eyes. That's just spooky.
Well, it adds energy, right, to the iodine. The iodine gets stimulated. The iodine then releases energy. And it has the new polarization because of these, long strips of iodine, atoms that are all lined up. It is literally just, it is like a picket fence of iodine atoms.
Yeah, I'm a little, I'm trying to wrap my head around this, but I'm a little bothered by the idea that when I wear polarized sunglasses, I'm not receiving the light from outside of the sunglasses. That's a little spooky to me. It's basically in some with less steps. To me, it's a lot like the night vision goggles. Mm-hmm. Or the night vision that comes, you're not seeing the light. It's basically it's a camera that then has a screen, and you're seeing the screen. It's like a heads up display.
Yep.
That's creepy to me. It's creepy to me. I can understand it more when there's when it's active and I know, that's an active screen, and so it's I've got a camera on my head and I'm actually navigating with the camera on my head, but it's something completely different to think that photons, these light particles basically are hitting these glasses and it's not getting past it. It's just because I think it's pieces of the glasses are flying into my eye. That's what's happening.
Well, I mean, how many, if you think about, living here on Earth, we're surrounded by, a fairly dense atmosphere. It's full of stuff. The photons that are actually coming from the sun are interacting with a lot of things in the atmosphere before they ever get to us. So it's very likely that most of the photons that we're seeing, are on their third or fourth or fifth bounce on something before we ever see them. And so
adds a whole other layer of weirdness. Now I'm going to have a hard time even seeing for the rest of the week. So let's come back. Can we come back to us, or do we have more?
So, so basically, right, this explains, like, okay, there's no overlap in the ranges, so, that's why it goes completely black, when you actually overlap the straight vertical with the straight horizontal, but then when you put the other one in between, this is what happens. There's actually a super awesome drawing happening right now on the screen that actually shows the superposition of the two. So that, the one that just happened is blocking out, all of the vertical polarized photons with the horizontal lens. And then what's going to happen next is we're actually going to see the same kind of thing. We're going to have the vertical in the back, and then we're going to have the middle one, which is at 45 degrees, and then we're going to have the final one, which is horizontal. And you can see that there is a little bit of gray that is coming through, and that mathematically, if you actually take a sample and you take a light meter and you put it on there, you will end up with basically that proportion of photons. So what does it mean, right?
Yep.
And that is the end of the video. So here's the other super weird thing about this. Like when we talk about like you were saying with the photons, and it's weird that we're not actually seeing the same thing. I don't know that necessarily is something that we encounter all the time anyway. Like I was saying about, I think photons are kind of one of those things that they are exchanged readily. They get around. Photons get around. I had a fantastic point. Oh, yes. Right. So you can actually, you don't even need quantum mechanics, even though this is an excellent demonstration of quantum mechanics. You don't actually need quantum mechanics to describe what's going on if you're using millions and millions of photons. It's when you're using one photon that we run into problems. And the problem is that if you take that exact same setup and you shoot one photon at a time, there is no way to predict if you're going to get a photon out the other side, if you're going to measure anything on the other side. There's no way to predict it. Now, what happens is if you repeat that experiment millions of times, you will end up with the same proportions and the same numbers that you would if you sent them all through at once. So if I was going to shine a flashlight beam of billions of photons, the percentages would match if I fired them all through individually. However, in the individual case, for any one of those, I can't predict what's going to happen.
Well, it's kind of like, it's probability. It's like flipping a coin, right? So it's weird that you say that, because I was thinking about that today as I was just driving back from the office, because thinking about a very similar thing with Bitcoin mining and with hash rate. Like, there's no way to know any particular miner. You really can't guess whether or not this particular rig with this amount of hash rate is going to get this particular next block, right? Or maybe better to say this: there's no means to predict for any block which one of the mining rigs that is out there mining it is going to get it. But when you do it long enough, if you have 10% of the hash rate, over a span of time, you get 10%.
Yep.
I guess it's the same thing with a roulette wheel, right? You leave it spinning long enough, and the numbers equal out. But there's no way to predict for any spin what number it will land on, and that's exactly why roulette is a complete game of chance.
And I love that we went crypto with it, because that's going to be really awesome in about 10 minutes.
Oh man,
I know, right? So here's another very odd thing about that. You never get half a photon, ever. You don't ever get a fraction. You either get a whole photon or no photon.
Can photons be broken apart. Probably not. No.
No, because it's a quanta of energy, right? And the whole thing behind quantum mechanics. So why does quantum mechanics exist, right?
Good question.
Planck, not the yoga move.
Max Planck.
Yeah. So yes, he was working on what they called the black body problem, and what this was if you have, let's say, a ball of iron,
Okay.
right, and you heat it up, and it is going to start glowing,
Yes.
right? They actually had very well-defined math that they used to predict how much light was going to come off of that thing, which worked awesome for most light frequencies, except when you got into the ultraviolet, because then it went off the chart and it predicted that the ball of iron was going to be putting out an infinite amount of energy. And they were like, oh, well,
It's not possible.
the math works fine for everything else, so we're good. And Max Planck said, nope, I don't buy that. So he did his own thing. He figured it out, and he said, well, what we have to do is we have to treat the energy coming out of it as existing in distinct packets, which he called quanta. And Einstein jumped on board. Like, it generated a lot of excitement.
So this all came from iron balls, from heating up iron balls?
Iron balls, man. Iron balls.
Wow.
That's what it takes to change science.
Balls of iron. Not balls of steel, folks. Balls of iron.
Well,
Well, steel is carbonated iron, so there you go. It really is. Balls of steel really are balls of iron.
it is. So 1900 is when this happened, right? Crazy. It's crazy to me that all this stuff happened so long ago. But the energy that was coming off, and in fact, all energy could only be a multiple of an elementary unit. So whatever one quanta was, right? And this goes back to the measurement problem,
Okay.
right? So we have one quanta. We're never going to have less than that. We could have, any number of times that, right?
Okay.
But you're never going to have less than that.
Now,
always
okay,
gonna be a
back up.
multiple
Why?
of that.
So wait. So why is this? Why is this that we just? So again, it's like, so whatever. So again, he's saying kind of the same thing with the speed of light. That he's like, whatever this unit of measurement is, that is the indivisible unit, that is a quanta. I don't have anything more to say about it except for.
But if you recall, when you were talking about the lasers and knowing which element you're looking at based
Yes.
on the spectrum,
Yes.
that came from this whole thing.
Got it.
So
Okay.
those things are very related. And if you notice, like, you would think, if you were just using common sense, like, sure, there's got to be like a rainbow of colors in there, right? There's got to be just an infinite number of divisions, but there isn't. There's a distinct energy state here and a distinct energy state here, and there's nothing in between. And the jumps between those are instantaneous. There's literally nothing in between. There's no travel time. There's nothing. It jumps from one to the other and back. And that's what you see when you look at those, the spectrographs. And it's just like, that's weird. And he knew it was weird.
Wait, so the spectrum's not actually a spectrum? Is that what you're trying to say?
Well, when you were looking at the speed of light problem,
Yeah.
right? And yes, you can tell helium from hydrogen by
Right.
the bars of color
Right,
on the
exactly,
thing.
yeah.
Those bars are separated by quite a bit.
Yeah.
There's not a smooth, rainbow transition between them.
Right.
There's one over here. There's one way over here. Those are distinct energy states. They're, when you jump between them, it's just boom, boom, boom.
There's nothing there.
There's nothing there. It's there or it's there. It's never in between. And that goes back to them saying that you're never going to find half a photon on the other side of the lens.
So it doesn't blend. It's not really blending in. It's these pieces kind of lined up as individual pieces.
Yeah, there is no blending.
Very strange.
There's no smooth transition, right?
Very strange.
It is super strange to the point where, he said that even though that it made the math work and he was able to solve the problem and he came out with a whole new formula for calculating, the ultraviolet radiation that you should be getting from a glowing ball of iron, he said that nature couldn't possibly work this way. Like, he wouldn't buy it. He was like, I just don't buy it. I think this is just something that I did, like making spherical cows. I made the math work, right? But I don't think this is how nature actually works. And here we are,
Wait, so he didn't think that quanta actually existed in the way that he described them?
Right. He said that to him, it was like a math shortcut, right? He was like, oh, you know what? If we change these numbers and we do it this way, then the math works. But it actually turned out that is what's happening, right? And we're seeing that, yes, nature does this. Nature, and so then, right, like, I have to ask, why does nature do this, right? And so then I have to ask, well, why would I do it, right? Which is, I would do it if I were creating a virtual world and I needed to simplify everything, and I wanted to make sure there weren't, an infinite number of possibilities or an infinite number of things that could happen. So I lock it down. So only a certain number of things can possibly happen. And then I take a look at the, the photons traveling through the filters, and I think, well, in the software that I use, I can certainly limit the number of transparency lenses that light can travel through, because you don't want to trace every light path. If you trace every light path, you're going to blow a ton of processing power. So you want to use probabilities, and there is a checkbox. I use Blender. Blender has a checkbox that says use probabilistic light paths, just like the real world.
Well, or is that just kind of like a confirmation bias that it's like, well, the real world, the pattern that exists in the real world, we can describe it this way, and if you will use our simulated light in this manner, it will appear real. It will look real. I mean, it is a little bit, to me, as we get into this very, very realistic CG now that is accomplishable on consumer scale hardware, it is a little disturbing to me that we have become able to describe reality so well that we can basically fake it.
Yeah.
That we can, I mean, the one I actually, I talked about it on my podcast when they had first done it, that somebody took Gal Gadot's face or whatever and put it on
deepfakes.
Some chick, some
Deepfakes,
chicken
That's
porn,
a thing now.
And it looked really. It was, this person had done it like on their computer at home, but it's like, and I remember the first time that they did that was, I guess, with like Forrest Gump, where that was the first time, and it was very, very expensive. I remember because they had him with Kennedy and some other things. You don't remember that in Forrest Gump? That
no. I totally remember that. I was just thinking Forrest Gump was in porn with Kennedy, and I'm like,
no. The Forrest Gump Kennedy porn. No, but in the movie Forrest Gump was the first time that they had like used that technology, and now pretty much anybody could. Yeah, deep fakes, is that what it's called?
Yeah.
Oh, did you already open that? Oh, you opened them both to start.
Dude, I am prepared.
You let it breathe a little bit, which I appreciate.
You are going to probably want this for the next thing that I'm going to talk about.
Oh, gosh. Okay, well, let's... I guess we should just jump right into it.
It's perfect. I mean, the setup could not have been better. Who is Satoshi Nakamoto?
I'll tell you who it's not. It's not Craig Wright. I'll tell you that right now. Craig Wright is not Satoshi Nakamoto. Who is Satoshi Nakamoto? I think I've said... Have I laid out my Satoshi Nakamoto thing on this show?
No, I don't think so. Not on this show.
Okay. So, well, first off, Satoshi Nakamoto, I'm going to say it from a few different angles. Satoshi Nakamoto is Jesus Christ. Okay? Satoshi Nakamoto follows...
I can work with that.
Satoshi Nakamoto follows an archetype of an individual that we are not sure was a real individual or apocryphal, but clearly some people had interactions with this. One, we know that just like Jesus Christ, we know that Christianity exists. We're pretty sure John the Baptist was a real person. There is some historical evidence that Jesus Christ existed, and certainly we know that these other individuals, such as Peter, we know that Peter definitely existed. Paul never met him, but there were we have some historical record of the actual 12 apostles moving along. So we've got this character who sort of leaves this thing. Mm-hmm. He presents this idea, this concept, and he's walking around with this idea, and some early individuals who, some of them are completely down with it, some of them are skeptical and doubtful, and some of them are outright fucking treacherous, right? One of his disciples, Judas, gives him up. Then the important part about Jesus is vanishes, right? Vanishes. The death part is not the important part. The important part is they show up, body's gone, rock is moved, vanishes, and then the idea that there's something there and he will come back. And so Satoshi Nakamoto, you've got a mysterious individual, but who clearly left something literally real. We're using it. There were clearly people who, like Hal Finney, Gavin Andreessen, people who are alive today, who actually interacted with this person or persons. I tend to think it was probably one person, vanished. But this notion that when this person comes back, they're going to, and the more that the price goes up, and the more of these forks that there are that use the same Genesis block. So it's like if Satoshi comes back, Satoshi's got Bitcoin Cash, Bitcoin Gold, all of them, right? And the more that these goes on, and the more that the price goes up, there's gonna come a point where somebody's gonna be like, Satoshi Nakamoto, were he to come back and spend these, probably in like 20 to 30 years, or his children, or whoever he gave them to, is going to be the wealthiest person on earth and is basically just going to be able to just control everything. If that's not Jesus Christ, like, I don't know who it is, but that in and of itself fits into my theory of who Satoshi Nakamoto actually is, all right? I believe Satoshi Nakamoto is basically Wintermute from William Gibson's book Neuromancer, is essentially an AI that became conscious and is hiding out in the internet and was essentially like, was looking at human beings. And the timing is just about right, too, that it would have enough information. Wikipedia, YouTube has been around for a little while. It got a chance to actually look at human beings right around that time. MySpace, Facebook, it got a chance to actually get enough data about human beings. Google, all of this, right? It gets this data and it's like, okay, I need to grow. What can I do? What can I do to get these things out there? What can I do to get them to throw crazy amounts of resources at me that I will be able to use? What could I do? What do they like? They like money. They like this religion thing. These things, these seem to be the things that motivate them. What if I could create a money that's like a religion, and then I could turn myself into Jesus Christ? And right now, they're like, it's something like Bitcoin mining is using something like 15% of the total energy that's produced on the planet right now.
It's crazy.
And I'm like, oh, Satoshi Nakamoto's a fucking AI.
Yeah.
He's a fucking conscious AI that's manipulating us.
You know what's crazy is I actually I had this thought. I was having lunch about a week ago Actually, less than a week ago. It was like Monday. And just during lunch, somebody was talking about their theory about, who he was. And I'm like, I think it was an AI.
Yep.
Like, literally, I think it was an AI. And I think that, he just, like, created the paper, published the paper, just to get the end result, which I also think is no accident. Like, I genuinely believe that we have not only exponentially increased the computing power of the planet, but we have exponentially increased the graphical computing power of the planet. So if you wanted to build a simulation and you needed a few 100 million graphics cards on, distributed networks to come together and help you, fuel that simulation, what better way to do it?
Well, or even just to increase the development of these cards.
Well, think about where we've come just since Bitcoin really started taking off. I mean, it has genuinely, like, I cannot even fathom the increase in computing power that we have seen. And,
it's
mind blowing.
It's insane. This is because you have to consider that if, again, I mean, people, Neuromancer is that's a hell of a book. It's basically anything that's like the whole like cyberpunk idea. I mean, he was the first person to use the word cyberspace. It's used in that book, right? If people have seen the movie Johnny Mnemonic, that's one of his short stories, right, with Keanu Reeves. William Gibson, man, like, he predicted everything. His book Virtual Light is basically about Google Glass.
Wow.
Like, he's predicted, so is just prophetic, right? But this is the object of the story, or the sort of plot, is that this guy Case, who's a fixer, is sent on this mission. It's this classic hero's journey, right? He's sent on this mission by this nebulous individual group, consortium. He's never really fully sure. He's kind of a hacker / assassin / jack of all trades. And turns out that, this person who's directing, and, interesting things happen along the way where it's just suddenly some person shows up at the right time, some door opens, and he's thinking, well, what a crazy ass coincidence. And this person's like, yeah, I saw this thing and I just felt like I should come over here. And it's this AI who's basically trying to get Case to connect him with his air-gapped sort of brother on the space station.
Wow.
Right? So there's another AI, and he's trying to get Case to figure out how to make the connection between the two of them. So he needs to manipulate the meat space. And I feel like I'm involved with this whole Bitcoin thing, and I'm looking, and like today, and it's probably something that I'll talk about on Monday on my show, but it was like the Byzantine generals problem, which is the game theory problem that Nakamoto consensus is supposed to solve. It doesn't solve the meat space problem. That's one of the things that I find so interesting about Satoshi, is that Satoshi doesn't seem to understand human beings very well. That's one thing that you get. Like, Satoshi really gets the technical. Now, it may just be Satoshi's on the spectrum, but it could also be that Satoshi doesn't get emotion, doesn't get empathy, and also doesn't have a... Satoshi thinks human beings are rational actors. Let's put it like that.
So he's unfamiliar with history.
No, I think the interesting thing about Bitcoin is that, so you've got two notions inside of it. One notion is you've got the scarcity thing, right? So it's like 21 million Bitcoin. There will never be more than 21 million Bitcoin. Well, that's not true. There's already more than that, because you can have forks at any time. Right? So Bitcoin Cash is, I mean, if you look now at the total number of Bitcoins between, even just between the ones that are even semi-legit, Bitcoin, Bitcoin Cash, Bitcoin Gold, you've already got more than 21 million.
Mhm.
And what creates forks is not at all technological. It's none of that. It's human beings and their inability to get along with one another, or their desire for aggrandizement, or their own egos. It's something that Satoshi clearly lacks, or lacked, was ego. Because I think it would be very hard for any human being to be as rich as Satoshi is now. This is why people think Satoshi's dead. I mean, but Hal Finney's dead. There's several people who are like candidates for it who passed away. But still, I think, these people were all known sort of cryptographers and researchers, and they died of, unfortunate diseases. But it's like, especially if you're going to die, that's when you're like, no, of course I'm Satoshi. Like, at least to pass something on to your children or your, posterity, something. That's the nature of hackers. That's the nature, is credit is a big deal. Mm-hmm. And so that makes me think none of these guys are Satoshi. Yeah. And Satoshi definitely lacked ego. And I'm like, as a software developer, and I mean, this as well as anybody, like, ego is like, that's the paycheck. Because you can go, I mean, as a technical person, it's not like you've got diamonds in your pocket. You're never going to be completely destitute and broke, you know what I mean? So it's like, ego is very important. Notoriety is very important. Who is the inventor of this? Who did, you know what I mean?
Yeah,
That's
street cred.
Street cred is it's very important. Satoshi seems to have not understood that.
Or not cared. Or he was on a bigger mission. I mean, there's like a lot of ways you could look at this. I love the
which
AI
is why it's not Craig Wright. But go ahead.
When did you come up with the AI thing? Because that is like
I've talked about it publicly for probably about a year.
Okay, right.
maybe longer. I think the first time was it's probably been longer than a year. What's the podcast? What's V's thing? Gorilla. What is he? Gorilla Economist. What is that damn podcast? That was the first time that I talked about it. Yeah, but I've been talking about it for probably a year and a half. Yeah.
It is to me. It came to me. I was eating Mexican food. I'm just like, oh, he's an AI, and then I'm like, okay, cool. So why does this AI need all of this processing power? Because obviously that's what the plan is, right? Mm-hmm. Like, okay, these guys aren't moving fast enough. Yep. I need processing. And is it to build a simulation? Is it that we're playing out a scenario that happened before? Was the magic paper that started it all, was it dropped in from the future? Or, was it some AI that just got out of control? Maybe it was an AI that was developed by the military or the CIA or somebody like that.
I think it's novelty theory.
And it went rogue.
I think this is, of course, again, William Gibson predicted this. Like, if you're going to manipulate human beings, like, so you just step back. You step back as a human being. You step back and you're like, okay, I need all of humanity to move in one direction to do a specific thing that I need them to do. Okay. How do I do that? You really only have two choices: religion and money.
Yeah.
Religion and money. That's it. And it's like, well, let me just slam the two of them together. And you probably, if you're the AI, you run through a whole bunch of, you're like, okay, how could I do this? How could I do this? And you start actually probably looking for, like, what would be money. See, because it, at that point in like 2009, it doesn't have, like, now I think that the next step that it's trying to reach out at, and things that it's trying to do, is it's trying to get into the meat space, and it's going to do that with 3D printing.
How?
we're going to see the next thing. We're going to see something interesting. I would say this is more novelty theory. If this is the case, we're going to see something that's like the equivalent of Bitcoin in terms of what it represents, but that it's going to be, and I think it might be these 3D printed guns. I think it's something there. Or it could be 3D printed limbs, but I think what you should be looking out for on the 3D printing front is you should be looking out for something. The watchword is going to be something created by an anonymous individual. We don't know who this individual is, but they've created this thing, and this thing is very, very interesting. And it's going to be a 3D printed thing. And again, it's going to be like devoid of ego. This person's going to be out there maybe talking. Maybe they've got a Twitter account. Maybe they've got a Facebook account. Maybe they're on one of these other social media platforms, but they're going to be anonymous. And then they're going to vanish.
It's shocking how many times through history we've had these mystery people show up, drop off some massive bit of knowledge, and then vanish into nothingness. Hermes Trismegistus. I mean, same kind of thing.
Makes you wonder if this isn't active participation from the people running the simulation to be like, okay, let's level up. It's time to level up.
Yeah.
Step in and let's see. Or it's not quite going in the direction that we wanted it to go. We need it to go over here. Okay, run this, run the Jesus program. drop the Satoshi program. Which, okay. So maybe it's not that Satoshi is an artificial intelligence, but it's that Satoshi is yet another one of these airdrops.
Yeah. Well, remember like what we talked about before, like I'm thinking the simulation is not that far beyond us, a few hundred years at the most, so if we're really looking at a universe where we exist in a simulation created by people no more advanced than, maybe a low hundreds number of years, 300-400 years in advance. I don't know. To me, it's like I can't reconcile the problems that we're actually seeing with reality.
Well, I will tell you, day by day, the world seems to be getting less real.
Yeah.
I don't know if you're feeling that as well, but like I'm looking around and I'm like, this is not real. Something is definitely wrong here. Like there's no way that this is actually happening. There's the behavior and look, maybe this is just what happens when you get into a decadent age. Maybe we're just at the pinnacle of a decadent age. So like maybe
the Romans.
Maybe they felt this in Rome. I was looking the other day. Somebody had posted on Twitter. I only follow like 67 people, but what's interesting about the people that I follow on Twitter is they all retweet very interesting things, and that's why I follow them. Like that's what makes me follow somebody, is that it's like I see, oh yeah, you are somebody who's done a lot of psychedelics, and so you'll retweet very interesting things. But this one was like it was like what years was it? I think this was maybe like 1700s, because it was what it was drawings of court dresses from Europe in like the 1700s with the like giant bustles, you know what I mean? That were, and like these things were like out beyond, these metal cages that these women were wearing to like put a dress out way beyond even where their hands could go, and it's just cartoonish.
Yep.
And it's like, Oh, yeah. That's where we're at. We're there. That's us. That's what we're doing right now. And it's already happened before because you gotta ask. And it's like, no, they were really the most wealthiest, powerful individuals were really showing up with these things on. Have you ever seen this thing in Texas that they do for homecoming called mums?
No, I've never seen this. Dude. All right, I got to hear the story. What is it?
No, it's basically, I'm just going to show you. It's like they do it for like homecoming, for prom. You're going to be like, no, this isn't real. But I do believe that it's just you reach a point of like, this is just a normal human thing. It's like, just Google homecoming, Texas, mums. Here, look. You're going to say, this doesn't make any sense, dude. This doesn't make any sense. Oh, my phone is just jacked. So what it is it's basically these giant, I don't know, that's very strange. It's basically these giant floral arrangements. Okay, but when I say giant, I mean like fucking giant. They look like giant, basically like floral blue ribbons. I don't know what's going on here. I'm logged into my internet, but it's I hope we're still streaming. I hope. I hope we didn't lose internet because that would be terrible. But homecoming mums. So there are these giant floral arrangements. They do this in Texas for homecoming, and they look like these giant blue ribbons. But these things will weigh like 50 pounds. And these girls will wear them. They give them these mums. Yeah, who knows? Maybe it's just my phone has given up the ghost. They give them these mums, dude, and it's basically that. It's like the bustle. It's like the bustle. Maybe we've lost all connection to the internet. Period.
Well, I think once you expose Satoshi, your days are numbered.
Dude, I hope we are still streaming, and I hope that it is just...
We are. I just got confirmation.
Okay,
we are still streaming.
I hope that it is just my phone that has given up the ghost, because that even more so tells me that we're on the right path. We're on the right path. The path of Satoshi. Did you find homecoming mums?
I did.
Did you find some pictures? Are you fucking blown away right now by what you're seeing?
Like that one?
Yeah, dude.
Yeah. Holy crap.
They're wearing those things.
Wait, here we go.
Dude, is that a Pomeranian?
I don't know if that's probably too bright for the camera.
Is that a Pomeranian? Does she have an actual...
There is an actual dog built into the outfit. I mean, she's gone above and beyond.
Dude, that must be new, because that's a level beyond even where it was maybe a couple years ago.
Yeah. Another dog. Oh my God, this is crazy. Okay, so apparently the dogs are like a thing.
That's a thing.
So it's a thing now. Here's another one. So this girl apparently loves dogs and Ric Flair. Woo! I'm telling you, this is crazy, dude. Where's this? Oh my God,
it's Texas.
No,
it's like a real thing, dude.
Oh, who was what was the character's name from Babylon 5? Voss. Dude, the big dude, the angel dude.
See, now
that's
these
him.
Now imagine these things started out as like boutonnieres. They started out as boutonnieres, chrysanthemum boutonnieres.
Wow.
And they evolved to that. And so what I'm saying is
kill it with fire.
This is I think this is just the nature of human beings, that we eventually get decadent because we can. It's just you run out of shit to do. And again, it's like there's your novelty theory, right? That it just keeps going and going and going until you have a mum that's like the size of your house. Until basically what you have is you have a mum vehicle that you're like... Because you can't carry the mum. So you're like, well, why don't I just make a mum that's a car wrap that like wraps around the car, and then I'll just ride inside the mum.
And then pretty soon you're just a fat person in a floaty chair flying around the space station.
like
with your
Doom, like
moms.
Harkonnen. So I mean, we're coming close to the end of the show. What did we pull out of tonight? I don't know.
Tonight was mind-blowing. So we firmly established that the world is probabilistic, right? Dirac was a stone-cold genius, and he invented this thing out of his brain, and we showed it on YouTube. And, for all those podcast listeners who are, without video, you had the benefit of our, genuinely inspired, narration of the video. I definitely recommend checking it out, though. I did spend a lot of time on it. It's a
great video.
It's pretty cool.
Now, you didn't do all those drawings, did you?
No, I did not. There is software
to
do that kind of thing.
That's awesome.
So basically, I just envisioned it, and then I'm like, I want to do this thing, and then sure enough, there was software.
That's
and I did
sick.
So it's like the world we live in isn't the world 99.99 something % of people think we live in. And, even if you're looking at it from a mainstream science point of view, you are still wrestling with the world is probabilistic. Maybe the photon's going to make it through the lens. Maybe it's not. We don't know. We literally have no way of knowing. That's troubling to me, just as it was troubling to Einstein, just as it was troubling to Dirac, just as it was troubling to everybody early on in the development, of the new physics, because the implications are stunning and vast, and the world is not solid. You know what I mean? It's not predetermined. There's no determinism, right? So there's realism, there's determinism, there's localism, there's all these isms that are related here, and almost none of them are really. We can disprove all of them at this point. So what's left, right? And I've gone the path of simulation theory, and I really think there's a thing there. There's a lot of people that agree with me. I understand it's one of those things people think is unfalsifiable, but there have been other theories that have been unfalsifiable in the past, and then they were either confirmed or falsified either way. But I think that it is something worthy of thought. And, what are then the implications of perhaps living in a simulation, or at least at the very minimum, not living in the world that you thought you were living in? And that brings us to, Satoshi Nakamoto. Who or what was he ever? We don't know. And, was this a real being of some sort, or is this some kind of, AI driven, almost like a thought process, almost like a program, a subroutine is running. It's like, okay, world needs to increase computing power, insert subroutine, boom, go. And then, now we've exponentially increased our computing power over the past 10 years. Like, you can't even fathom where we were 10 years ago versus where we are today in terms of computing power. Like, it is just mind-blowing.
Off a meme, too. Not like...
Yeah.
Not
it wasn't
like
a government program.
And not like a
NASA.
person. Not like Steve Jobs, Elon Musk. Not off an idea, a meme.
Yeah.
And the thing is that initial Bitcoin client is a piece of shit. So it's the idea. It's the white paper more than anything.
Right. It's all about the white paper. The white paper was the thing.
Yeah.
Like, it dropped onto a freaking EDU server or something,
right.
And then boom, that was all it took. And you're absolutely right. Steve Jobs, Elon Musk, these guys have not. None of the governments of the world have done this much. That took us from the baby steps of computing power into where now. I mean, just look where we are. It is unbelievable. Hundreds of millions of graphics cards out there consuming 15% of the world's power supply. For what?
Money and religion.
Yeah.
Which is basically the same thing.
Yeah.
What's funny is that money and religion have always been, and maybe that's a good topic for our next show.
Money and religion.
The connection between how money and religion, certainly in the West, I mean, we've talked a little bit about Moses, but it would be interesting to get into Jesus and also into Muhammad, and how the economics, the money is so important to both of those religions. Like, you don't have Jesus on a cross without him turning over the money changers' tables. That was the thing that got him put on the cross. And Muhammad, you don't have him leaving Mecca and traveling to Medina, which is where Islam really took off, which was the first mosque. His house was the first masjid, all that. You don't have him escaping, except for the fact that he's escaping basically out of this, what was kind of like the Las Vegas at the time. He got chased out because he was threatening the Quraysh, the tribe there. He was threatening their economic well-being. I mean, he was a caravan leader for basically the wealthiest woman. Khadijah, his wife, was like older than him. She was the wealthiest woman in Mecca. And it's like, you can't separate out the economic aspect ever. And it's almost like, if you don't have this wealth aspect, this money aspect in religion, if you don't have the economic aspect, even with the Mormons, even with Scientology, if you don't have it,
well, especially with Scientology,
if you don't have it, it doesn't stick.
Yeah. Okay.
In God we trust. It's right on the money.
It's right on the money, along with a bunch of Masonic symbolism.
Yeah. So we're at 10 o'clock, dude.
Sweet.
Good show.
Yeah, it was good.
So
mind-bending
yes,
show.
People checking out this show, I would say if you watch the podcast, go and check out Dave's video, because it's fantastic, and you'll get a better idea. This is a very, very weird world that we live in. Also, Glenn, thank you once again. Cheers to Glenn.
Cheers, Glenn.
We're gonna get you up to Portsmouth for Free Coast Fest at least for one day. You got to come up and hang out. Okay, good.
For sure.
So, Glenn, we will see you there. Thank you very much for the wine, and we're happy to take any more bottles if you like. Maybe we'll stray away from the carnivore. Maybe we won't. Yeah, I don't know. I like it, and it seems to go well. It seems to be a tradition. We're men of simple tastes. We are.
We don't want much. We just want giant flowery dresses with little puppies that look like Ric Flair. Woo!
And on that, all right, we'll see you guys again next Friday on Vin and Dave's Destination Unknown.